Welcome to this explainer. I'm your host, and today we're diving into an absolutely fascinating final year project defense. I want you to imagine you're sitting on the evaluation panel, and stepping up to the podium is engineering group GB6. They're here to present REACT, which stands for the Renewable Energy Automated Control Trainer. Now, this isn't just your standard school project. We're looking at a revolutionary educational platform that integrates solar, wind, and hydropower, along with PLC automation, IoT monitoring, hybrid charging, and AI. It's designed to solve a really tough problem: how to effectively teach the chaotic, unpredictable nature of real-world renewable energy. Let's dive in and see how they pulled this off.
Section 1, Background and Problem. Let's look at the educational gap we're dealing with today.
So, why is this project so important? Well, modern engineering education is kind of missing the mark when it comes to hands-on renewable energy tools. Just look at the contrast here. Existing trainers usually just offer a single source, like a lone solar panel, with absolutely no industrial PLC automation, no IoT monitoring, and no interactive AI learning. REACT completely flips the script. It's a hybrid system that simultaneously uses solar, wind, and hydro, backed by robust PLC-based protection, highly precise INA 219 power sensing, smart IoT connectivity via an ESP32, and an AI chatbot. It's literally a mini smart grid. Section 2, Project Objectives. Here is the vision the team set out to achieve. The team was driven by 4 really clear objectives. First up, develop that hybrid generation platform combining solar, wind, and hydro. Second, implement a programmable logic controller, or PLC, to handle system protection. Third, build out an ESP32-based IoT dashboard for live monitoring. And fourth, integrate an AI educational chatbot. They didn't just wire some components together, they built a fully integrated smart educational system.
Section 3, System Architecture. Let's look at the power and data flow.
Let's trace the physical power flow first. It starts with our 3 sources: solar, wind, and hydro. That raw, fluctuating power flows right into the INA 219 sensors, and then into the PLC protection system. If everything's safe, the power moves through the relays, past the Schottky diodes, and merges at the hybrid charging bus. From there, a buck converter steps the voltage down to a stable level so the TP4056 module can safely charge the battery. It's a remarkably clean pathway from unpredictable green energy to safe, stable storage.
Now let's look at the data side of things. While the power is physically moving, those INA 219 power sensors are grabbing real-time voltage and current data. That data is fed to both the PLC, which acts as the protection brain, and the ESP32 microcontroller. The ESP32 then takes that telemetry and pushes it straight to the IoT web dashboard and interfaces with the AI chatbot. Everything is perfectly synchronized.
Section 4, Hardware Components. Let's see what went into the actual build.
Let's break down the hardware. For generation, we've got our solar panel, wind turbine, and hydro generator, paired with an RPM sensor, anemometer, and light sensor. To measure the power, we use those INA 219 sensors. The brains of the operation consist of the industrial Mitsubishi PLC FX3U and the ESP32, which control the relay module. Finally, for safe power management, we use Schottky diodes, a buck converter, a TP4056, and of course, our battery. It's a real powerhouse of components. And here is the physical result. This is the fully assembled REACT prototype board. And honestly, it's a thing of beauty. You can see how they've neatly separated the generation modules, control hardware, and the IoT processing. It really proves just how viable and complex this hardware build actually is.
Section 5, System Operation and Protection Logic.
So, how does it actually run? The system operates in a really tight sequence. Our renewable sources generate power. The INA 219 measures the voltage and current, and the PLC continuously monitors those thresholds. If a source gets overloaded, it's instantly disconnected by the relay. Meanwhile, the remaining safe sources just keep right on supplying power. That energy merges safely at the hybrid bus, charges the battery, and the ESP32 continuously publishes all this live data to the dashboard.
Let's dive a bit deeper into that PLC protection, because this is crucial. The PLC does not just pick the best source, and it definitely doesn't shut the whole system down if there's a fault. Instead, if it detects a voltage or current spike that crosses the safety threshold, the relay selectively isolates only that specific overloaded source. The remaining sources continue operating without missing a beat. This is industrial-grade automated fault isolation, exactly like what you'd see on a modern city grid.
Now, you might be wondering, how do multiple fluctuating sources merge safely?
The secret is Schottky diodes. Think of them like one-way valves. They absolutely prevent reverse current. This allows multiple renewable sources with similar voltages to contribute to one single hybrid charging bus simultaneously. Without these diodes, a higher voltage source could push current backward and literally destroy a weaker generator or drain the battery. It's simple, but incredibly effective engineering.
Section 6, IoT Dashboard and AI Integration, bringing it all online.
So the SP32 isn't just passing data along, it's literally acting as a web server. It hosts an HTML dashboard over Wi-Fi, providing students with real-time monitoring of voltage, current, power, and generator RPM, while also keeping an eye on the battery charging state. It gives users hands-on experience with the exact kind of telemetry you'd find in a commercial smart grid control room.
And to make this a truly next-level educational tool, they added an interactive AI chatbot. If a student is looking at the dashboard and doesn't understand a renewable energy or PLC concept, they can just ask. For instance, if they ask, "What is solar energy?" the chatbot instantly fires back with a clear technical definition. It's like having an automated, always-on tutor right there on the screen.
Section 7. Results and benefits. The proof is in the pudding.
The results from their testing phase were fantastic. They achieved successful PLC fault protection, safe hybrid battery charging, and flawless real-time IoT and AI integration. Plus, they managed to keep it low cost and highly portable. They essentially created a fully functional, highly effective smart grid simulator that's ready for the classroom.
Section 8, SDGs and Conclusion. Let's look at the bigger picture.
REACT directly contributes to several United Nations Sustainable Development Goals. By providing interactive, hands-on learning, it supports SDG 4, quality education. It heavily promotes renewable awareness, hitting SDG 7 for affordable and clean energy. And by training the green engineers of tomorrow, it's a direct contribution to SDG 13, climate action.
To wrap things up, Group GB6 absolutely nailed it. REACT successfully integrates multi-source renewable energy, industrial PLC automation, IoT monitoring, and AI into one cohesive educational platform. It perfectly bridges the gap between reading about these concepts in a textbook and actually managing them in a real physical system.